Wormholes. We all have this picture in our heads of these cosmic shortcuts, right? It's a total staple of science fiction, but what if I told you the real story is, well, it's a lot weirder and it has almost nothing to do with space travel? So let's just get on the same page. We think of a wormhole as a tunnel, a simple shortcut through space-time. You hop in one side and bam, you pop out light years away on the other. But where did we even get this idea?
Well, here's the thing. The wormhole wasn't invented. Nobody sat down and designed it. The real story, it actually began as a complete accident. It was a mathematical surprise that was just sitting there, hidden inside Albert Einstein's own equations.
And that discovery takes us all the way back to our first chapter, the accidental bridge. Okay, so picture this. It's 1935, and Einstein and his buddy Nathan Rosen are wrestling with a huge problem in physics, singularities. They hated the idea of an infinitely dense point, so they were trying to describe a particle, like an electron, as some kind of smooth feature of space-time. And while they were working, they stumbled onto something totally unexpected. In their own words, they found a model where a particle could be seen as a bridge connecting two sheets of space-time. And that, right there, became the Einstein-Rosen bridge. But what's so fascinating is its original purpose. This wasn't a tunnel for spaceships, not at all. It was a purely mathematical model of matter. It was like imagining two parallel universes, or maybe just two really distant parts of our own, linked together by this tiny, fragile little throat. But, of course, there was a catch. And, oh man, it was a big one. This so-called bridge was completely unstable. It wasn't a tunnel you could just waltz through. It would pinch itself off the very instant it formed. Anything, and I mean anything, trying to cross would just get crushed. So this is the key takeaway. The very first wormhole was completely, totally non-traversable. A cool idea, for sure, but a total dead end for travel. So for more than 20 years, that idea just kind of sat on a shelf. But then it got a major makeover. It was reimagined, not as one single bridge, but as a basic feature of a whole universe of foam. The story picks back up in the 1950s with this brilliant, kind of eccentric physicist named John Archibald Wheeler. He's actually the guy who gave the wormhole its name. And Wheeler, he had this totally radical new vision for what space-time really is. He basically said, hey, what if you could zoom in to the absolute smallest scales possible? The Planck length. Down there, space-time wouldn't be smooth at all. Instead, it would be this chaotic, bubbling sea of energy that he called quantum foam. And in this foam, tiny little wormholes would just be constantly popping into and out of existence, linking different points in space and time for just a flash. It's an incredible shift from thinking of this as some static math problem to a dynamic, living feature of our reality. Now, let's be super clear here. These little wormholes were still microscopic. And yeah, they were still non-traversable, snapping shut instantly just like the original Einstein-Rosen bridge. But what Wheeler did was a really big deal. He took the concept of the wormhole and baked it right into the fabric of physics. It wasn't just some mathematical curiosity anymore. It was a potential piece of our universe. And for another 30 years, that's pretty much where things stood. That is, until a huge breakthrough moment when scientists finally sat down and asked, okay, forget accidents. Could we actually design the shortcut? Just look at this timeline for a second. You've got Einstein and Rosen's accidental bridge in 1935, then Wheeler's quantum foam in 57, and then boom, a massive leap forward to 1988. This is when two physicists, Kip Thorne and Michael Morris, published a paper that completely changed the game. So just how different was their idea? Well, the contrast is, it's just night and day. The Einstein-Rosen bridge was an accident, a way to model a particle, and it was always going to collapse. The Morris-Thorne wormhole, on the other hand, was intentionally designed from the ground up to be a traversable tunnel. They literally started with the goal of how do we get through, and worked backward to figure out the physics. And what they found was a way to make it theoretically stable. But yeah, there was a very, very big catch. And this right here, this is the mathematical heart of their idea. It's called the Morris-Thorne metric. Now don't worry, we're not going to dive into all that complex math. What's important is what this equation represents. It is a monumental step forward. It's the first ever blueprint, the actual recipe for the geometry of a space-time that has a wormhole a person could, in theory, travel through without being instantly squashed. But like any recipe, that blueprint came with an ingredients list. And on that list was something, well, something that seems impossible. This brings us to the big twist in the story, the impossible ingredient. I mean, just think about it for a second. A tunnel through space-time is a tunnel through gravity itself. And what's the one thing we know gravity does? It pulls everything together. It crushes. So the very existence of a wormhole's throat means you're fighting this constant, overwhelming force that wants to make it collapse in on itself. So, to hold that tunnel open, you need something that does the exact opposite of normal matter. You need something that pushes outward. You basically need a form of anti-gravity to prop the doors open. In the language of physics, this means you have to break a really fundamental rule called the null energy condition. This condition basically says that for anyone, anywhere, the energy density you measure can never be negative. It's just a basic rule of the road. But to hold a wormhole open, you need the energy density to be less than 0. This demand, which comes from what's called the flare-out condition, is an absolute geometric requirement to keep that tunnel throat from collapsing. It's non-negotiable. So what kind of stuff has negative energy density? Well, physicists have a name for it: exotic matter. And this is our impossible ingredient. It's this purely hypothetical stuff whose negative energy would create a repulsive gravitational force, essentially holding the wormhole open from the inside. And here's the crucial part. It has never, ever been observed, and it might just plain violate the fundamental laws of nature as we understand them. So the whole design requires a substance that might not even exist. You think that's the end of the story, right? Well, not quite. Let's see what our deepest, most fundamental theory of reality has to say about all this. In our final section, quantum physics says no. Honestly, building a stable, human-sized wormhole faces this unbelievable list of challenges. I mean, finding exotic matter is just the first insane hurdle. Then you'd have to make sure the thing is stable, shield travelers from being torn apart by tidal forces, but all of that, it just pales in comparison to the killer constraint that comes from quantum physics. Okay, so here's the really wild part. Quantum mechanics actually does allow for negative energy to exist. The vacuum of space is fizzing with these quantum fluctuations that can, for a split second, have negative energy. But, and this is the absolute knockout punch, as physicists Larry Ford and Thomas Roman discovered, nature puts some really strict limits on this. These limits are known as the quantum inequalities. And they are brutal. What they say is that, sure, you can have a tiny bit of negative energy for a very, very short time, but you can never have enough of it for long enough to prop open a wormhole big enough for a person or a spaceship to get through. It's kind of like nature lets you borrow a tiny bit of energy from the bank, but you have to pay it back almost instantly, with interest. Trying to build a human-sized wormhole would require a loan that nature's laws simply forbids you from taking out. And that just perfectly captures the journey we've been on, doesn't it? We went from a mathematical accident in Einstein's notebook to a blueprint for travel that needs an impossible ingredient, and finally, to a fundamental veto from the laws of quantum mechanics. So it leaves us with this huge question. Are wormholes really truly impossible, or are they just waiting for us to discover some new physics that could completely change the rules of the game?